All right. So, all right. Um, Hello everybody. My name's Ditya. I am your director of physics here at Simple Tutor. I'm one of your instructors. I will not be your instructor for every class, but I will be for a few. I'm the one who has designed this course, and without any further ado, let's get straight into it. This is Introduction to Physics, and today we're just going to be doing a basic math review. Now, this isn't directly physics, but you'll need to know all these concepts to actually complete physics problems and do things like that. So you're going to want to make sure you're solid on these ideas and concepts. All right, so today we're just going to be going over graphing, the metric system, precision and accuracy, equations, quadratic, and trig. So let's just start off with some graphing. So many of you guys probably know this, but we graph y versus x. That means y is vertical and x is our horizontal. And another way to word this is that x is our input variable, which is our independent variable. And y is our output variable, which is our dependent variable. And this is important to remember because um, many of you may have just, done simple equations in math where you don't actually get different variables than y and x. But in physics and other courses you'll take in the future, you might get something like time or a different variable as your independent variable, as your input variable. And you'll get different symbols, different units. And it's important to make sure that we're not just graphing x and y, and we know what exactly we're graphing. X and Y are just really just symbols to represent independent and dependent variables. So we can take a look at this data set that we're given right here. We have, as you see, time, days, and number of bacteria. So when we get data sets for graphing, it's important to first determine which value is your input value. So between time, days, and number of bacteria, we can say that time days is clearly our input value because as time changes, the number of bacteria changes, and it's not the other way around. And therefore, your other value is going to be placed on the y-axis. And another important concept to understand is scaling your graph. You need to be able to use your minimum and maximum x value to scale the x-axis. That means we're going to want to start it somewhere around, but not after our minimum x value, and end it somewhere around, but not before our maximum x value. So therefore, we do not want to start our x-axis after number 2 or after the number or end it before the number 33, but we also don't want to just make it from, like, for example, 0 to 100 when our graph is only from 2 to 33. One big thing is that you do not have to start either of your axes from 0. You just need to make sure that your scale is linear. So overall, it can if your measurements range on the x-axis or the y-axis from like 500 to 600, you can start your graph from 500 and increment it to 600 linearly. It does not have to start at 0. So I think that's an important thing because people always tend to just start it at 0 even if they don't need to. But that's a big thing. You do not need to with your graphs. And then after you scale your graph, then we plot our data. Another important part when you're graphing is labeling your axes. You need to make sure you always label with a quantity and unit. This is something that if you take physics, and for example, if you take an AP course and you get a graphing question on your AP test, making sure you graph with the quantity and unit on your axes is going to guarantee you some free points that you would miss if you just completely neglect this. Make sure you have a title for your graph as well for the same reason. We title our graph in the form of y versus x, but of course we need to know what our y and x variables are. And for example, with our previous set of data, we can graph it as number of bacteria versus time in days. If you're plotting multiple data sets, for example, if I had 2 sets of bacteria, so if we go back to the set of data right here, if we have two sets, for example, of bacteria, not just one, that grew at maybe a little different rate, and we can call that our second data set. We want to use sort of legend or key to graph these multiple data sets. So it's a key is really a way of denoting which data set belongs to which, um, so that the grapher doesn't get confused, and then the reader doesn't get confused in the future as well. So it's just a way, like, you can do this by coloring your points differently, drawing a little shape on one of them. So just making sure you have the legend, and also incorporating that in your graph is important. So when we look at equations to graph, we always look at them in the form of y equals mx plus b. So therefore, we know m is our slope and b is our independent variable. To graph, really, all you have to do is plug in certain values for x. Typically in physics, we're not going to start in the negative x. We're usually going to start in terms of time, which is going to be time t equals 0 and beyond, or whatever time is given, but there's no such thing as negative time. So we can plug in values and slowly graph them. Sometimes they'll ask you to graph certain points. So we'll be able to plug in those x values and then graph them. And this is the same concept if you're given a linear equation that's not in the form of y equals mx plus b. Like a quadratic, parabolic, etc. Another important thing in physics when you're graphing is finding your line of best fit. Oftentimes we'll get a data set that's not exact, it's scattered a little bit. Like for example, you see in this graph right here, it's not entirely fit in a line, but we can create this line of best fit that gives us an approximation of how the graph is changing. So that, as I mentioned, the distribution may skew. An important thing to do is not connect the dots when you're trying to draw a line of best fit, because of course then you won't have a line. It'll be a lot more jagged and rigid. But overall, you won't be able to find a definitive slope. And it's really inaccurate if you try doing something like that. It's oftentimes something people just try to connect the dots, but you need to make sure that you don't do that. And another important thing when we're drawing this line of best fit is that it does not need to pass through the origin. It's another mistake that people try to make. They always try to draw their line, but then have it pass through the origin some way, and it really messes up their slope, and messes up their measurements, because your line of best fit, the way I like to draw my line of best fit is try my best to keep a line that goes through at least a few points of the data, but make sure we have an even amount of data on the right and left side. Sorry, 1 second. So we need to make sure we have a even amount of data on the right and left side. So as you can see here, we have 1 point really sticking out on the right side and 1 point that's not really touching the data on this left side right here. More or less, we see 2 points that, or really 3, if you consider that this is really touching, that really the line is going through. Of course, you won't always have a data set or skew that's that close. It'll a lot more times be more spread apart, that in a way that you can't really get many points on your line of best fit. But your idea is not really to get too many on that. It's really to make sure that it's accurate, because you need to account for outliers and things like that. So it's easy to find the slope and equation of the line of the best fit. All you really have to do is use your slope techniques that we've always used in previous math. Just really figure out the rise and run. That'll give us a slope, and we can also figure out where this equation intersects the y-axis, and that'll be our y-intercept. So our next topic here is going to be the metric system. So we're not going to spend too much time here. We do not need to memorize all these prefixes. If you want to. I'm not sure if you need to, but really the ones that we use from physics range from tera to nano. We hardly get into nano, tera, giga, mega. We mainly, like when we need to do conversions in metric, we normally get kilo, deci, centi, milli, micro. So you just need to make sure that we know how to convert from, for example, kilograms to grams. So if I have 1 kilogram and this is 10 to the 3, right? That means it's 10 to the 3 from the base, and we know the base unit is the gram. So therefore, 1 kilogram is 1,000 times the gram. So I can simply multiply 1 times 1,000 to get the amount of grams. And you can do the same concept, the same conversion technique to convert from any form, any prefix to the base unit to any other prefix by just understanding the difference between them. So it's important to memorize, oh, kilo means 10 to the 3, or mega means 10 to the 6, or centi means 10 to the -2, etc. And these right here, these are just some basic units that we're going to encounter in physics oftentimes. So these are our base units. So when we use distance, we're normally going to be using meters. So if you are given a measurement in kilometers, the question may not directly ask you, give me this answer in meters, but it's important that we realize that if it doesn't ask us for an answer in a specific unit, that we revert to our basic given requested units. So when we're given distance, we need to make sure we answer in meters unless specified otherwise, and etc. for these following units: time, seconds, mass, kilogram, electric current, and electric charge overall don't matter too much. They're just in this chart. When we're dealing with physics mechanics, we don't really need to worry about that. But temperature, Kelvin, force, Newton, and energy, joule. And energy, joule is the same unit for work, which is the amount of force exerted over a period of time. We're going to be getting into that a lot later, but these aren't every single unit that you're going to use, but these are the um, main units that you're going to need to know. So now that we can get into a little bit of precision and accuracy. So accuracy versus precision. So accuracy is how close a measurement is to a known value, while precision is how close multiple measurements are to each other. Oftentimes we get these definitions confused and we don't really know which is which. It's important to make sure that accuracy is how close a measurement is. Really a good way to envision that is, for example, we have a measured value of a pillow. We'll say that our known value, it's just completely random, is 2 pounds. And we measure a pillow and we find that value to be 1.9 pounds. Therefore, it is pretty accurate within a certain error, but overall, it is very close to the value that we are given. So therefore, that measurement is accurate. If we measure that same pillow different times, but for some reason we get 1.9 pounds one time, and then another time we get 1.1 pound, and another time we get 1.5 pounds, overall, those measurements are not precise because those multiple measurements are not close to each other. And this is an important concept to understand when we're doing labs in physics, which is a very big part of the course. We won't be doing many labs here because, of course, it's virtual. But if you were to take the course in a classroom setting, etc., you would be partaking in many labs. We need to understand, are our measurements accurate and are they precise? And therefore, these two factors determine if our measurements are reliable enough to use in data to do a report, or do we need to redo the lab because we may have followed a procedure incorrectly. So I want you guys to take 2 minutes right here. So I have 4 different scenarios. I want one of you guys at the end of this 2 minutes, I'll ask you guys to raise hands to tell me, are these measurements accurate or precise? So how accurate is it and how precise is it? I just want very accurate or not accurate. And the same thing for precise, just really 2 descriptions for each one. So I'll come back to you guys in 2 minutes and let me know what you guys think. Okay. So if someone could raise their hand or unmute, now would be a good time. Just let me know what you think. Yeah. All right. All right. Darsh, if you want, you can go.
So the first one, it looks accurate and precise
Okay.
because it's all the dots are pretty close to each other,
Mm-hmm. Yeah.
and that means that it would be more of an accurate answer.
Yeah. Okay. There you go. Number two.
For number two, it's like the same thing because they're pretty close to each other.
Okay.
So
So
you also, yeah, it's
okay,
like
so they're close to each other. So what does that mean? Like, are they precise? Are they accurate?
they're gonna be precise and accurate
Okay.
because they're close together, so you could get like a correct
Okay.
measurement.
So right there, you are right that they are precise because they are known. They're multiple measurements and they are close to each other, so therefore they are precise. But they're not accurate because in this scenario, we're considering the middle, the origin, to be our measured or known value. And these values kind of stray away from that origin, and they're a little bit more to the top right.
Hmm.
So therefore they are not accurate. So it's important to remember that we have, for example, a known value for really everything. And if we measure something and it's a little bit off, therefore it will not be accurate. But if we repeat that measurement and we get the same measured value every time, then it is precise. But accuracy is based on, I think important to remember, accuracy is based on previous and already done measurements that are a set or known value, but precision is based on repeated trials of the same experiment or the same measurement. Um, I'll have someone else answer the next two. So I'm Rashik, I'm not sure if you have a question or you want to answer the next two, but you can go ahead.
I'll just answer.
Okay.
So for the third one,
Yeah.
uh, the it's the dots are somewhat precise, but they're not really that close to each other,
Okay.
and they're somewhat circling around the center, so they're somewhat accurate.
Okay.
And then for the last one, they're not actually precise or accurate because they're separated and put in random positions, and most of them seem to not are pretty far away from the center.
Okay. Yeah, you got the idea. Um, we again, somewhat, we don't need to dive into somewhat versus very versus much. We just want to worry about like is it accurate? Is it precise? Uh, as you said, the dots in the third example sort of go in a circle around the center. So they're pretty accurate. They're not entirely accurate, like for example, the first one, but they are somewhat, as you said, accurate. And of course, they are not very precise either, because they are kind of spaced around each other. And then like the first value, like each value is sort of a little different from each other. And as you said, in the fourth value, they're not accurate or precise because they are not near the center and they are not really near each other at all. They're really spaced out throughout each quadrant. But overall, that's the main idea. Precision is how close measurements are to each other, while accuracy is how close measurements are to a known or correct value. All right. Okay. Give me one sec. I don't. Okay, there you go. It was like. All right. So now another important concept is looking at error. Sometimes again, values don't match. This could be between measured values and known values, or measured values really comparing precision and accuracy in both aspects. So sometimes we need to determine our percentage error to determine, can we really use this value? Is it valid to use? Or do we have to repeat the experiment again? And the formula for percent error that we use is measured value minus expected value over expected value. And it's the absolute value of that times 100. So right now, I am going to just quickly go into, hold on. Yeah, hold on. I need to stop share real quick and share a different screen. Okay, here. I'm gonna quickly use that same idea, that same percent error formula. I just want to show you guys how exactly we're going to use it. So as you said, just it's pretty simple. Just follow this formula right here. So we have measured value minus expected value over expected value. Okay, so let's say our measured value for the weight of the pillow was 1.9 pounds. And our expected value was 2 pounds. Let me just make this a little bit. So our expected value is 2 and our measured value is 1.9. Simply, we would just plug it in to this equation. So it's 1.9 minus 2 over 2. And make sure we always take this absolute value because otherwise we'll be getting into negative percentages. And of course, we cannot, those do not exist. So this is simply the equation we have set up. So it becomes 0.1 over 2 times 100. So if we want to just cancel out, we can just cancel this, make this 50, and do 50 times 0.1, which is simply 5. So therefore, this tells us that if our measured value is 1.9 pounds and our expected value is 2 pounds for the weight of a pillow, that our percentage error is 5%. And therefore, our measurement is probably accurate enough to use. We might want to repeat this trial a few times. If we get sort of variation in our measurements, then we might have to redo our experiment, consider our procedure. But this value, if we were only measuring this thing once, this value is pretty accurate. Now, based on what your percentage error is, you're going to have to make a judgment call if this value is accurate enough to use. There isn't really a set percentage that a measurement can vary by, but based on the quantity and size of the value, you sort of have to come up with an idea. Is this measurement usable? Is it not usable? Jayadeba, do you have a question?
Yeah, wait, so couldn't you just do like the measured value over the expected value and then subtract subtract that fraction from like 1, and then wouldn't you get like a fraction and then you turn that into a percent and then that's your percent error?
I believe you can do that because this is just the way that I think physics, this is the basic formula they teach you. There are probably different ways to calculate percentage error. I believe, yeah, there's probably some way if you factor out the 2 and you subtract it by 1 instead. But this is the main formula that we do use in physics. So if they do ask you in many cases to show your work, this is usually the formula you want to go to. If you are more comfortable for the purposes of this class, if we have percentage error questions, if you are more comfortable with a different formula, you're welcome to use it. But this is the main formula that we are going to use in physics. So again, the same idea is, getting back to it, is that you're going to have to make that judgment call to know, well, can I use this value? Can I not? So let's get back to the slides. Okay. And we can, as mentioned, this is not something that we're really requested to do as much in physics, but we can find the error between different measured values. So this is the formula for that. Value 1 minus value 2 over the average of value 1 and value 2. This is simply 1/2 times value 1 plus value 2 times 100. And the reason we find the averages is to make our measurement more precise, because we're measuring between 2 measured values and not 1 known or expected value, which is inherently correct. We are not required to do this much in physics. You guys, that's why I'm not going to really get into it in the practice. You guys are welcome to memorize this formula, but of course, I don't believe you need to. I've never encountered this in a physics problem. But the main one we have to remember is measured value minus expected value over expected times 100. Okay, now let's just get into some basic equations. So our most basic equations, these are our single variable equations. So the tactic to do for these are just simply isolate our variable and solve. For example, 3x minus 3 equals 15. Therefore, we can just isolate by adding 3 to both sides. 3x equals 18, and therefore x equals 6. Now, I'm going to give you guys 2 minutes to solve this equation. It's pretty simple. Use the same idea. And then I'll ask one of you guys to explain to me your steps and tell me how you got there. Devansh, do you have a question or do you want to solve this right here?
Solve it.
All right, give me 1 second. I'm just going to open this in Paint just so I can show your steps. Okay, so our equation is 9x plus 20 equals 101. All right, so tell me how you solve this.
So first, what I did was 101 minus 20, which is 81.
So
So
let me
then-
let me click this down. So 9x, you got to 9x equals 81, correct?
Yeah.
Okay.
So then I found that I did 81 divided by 9 equals x, and so x equals 9.
Okay, there you go. You can just simply get x equals 9. Simple equation. You guys have probably done this 100 times, million times before, but it's important just to make sure we get our basics down. Let me get back to it. Honestly, I'm just going to share my screen, make it easier. Okay. Now, these are our 2 variable problems. These are systems of equations. So the way we do these are we solve for one variable in terms of the other in one of our equations, and we plug that into our other equation and then solve for that variable. Once we get an answer for that variable, we can sort of go plug it into either one of our 2 equations and find the variable that we do not have. So for example, x plus y equals 5 and 2x plus 3y equals 6. Using the first equation, we know that x equals 5 minus y. We can just plug in into 2x plus 3y equals 6, just plug in x equals 5 minus y. So 2 times 5 minus y plus 3y equals 6. 10 minus 2y plus 3y equals 6. 10 minus y equals 6, and therefore y equals 4. Ishan, do you have a question or?
Can't you also solve by elimination?
You can. That you can like add and subtract your equations, but that's not always going to work. Certain scenarios you're going to get sort of 2 equations that you're going to have to solve for in terms of the other, and especially in physics, you're going to be getting equations that usually they don't let you solve by simply eliminating them, because I think that's a more simple and basic technique. They're going to ask you to solve for one variable in terms of another and then plug it in. I feel like it tests more of your ability to not mess up simple math calculations. So for the purposes of physics, this is the main way we know how to get into systems of equations. As I mentioned, of course, this is not a math class, so we're not going to be getting into every technique. Of course, you guys may know other techniques to solve certain math problems, but we're not going to be getting into every technique. Of course, it's physics, so we want to get into the techniques that are going to be tested and are going to be asked for and going to be, you're going to be told to do this and to get this. So we want to make sure we get these techniques solid. If you know another technique, of course, that's great, but these are the main techniques that we want to use.
Oh, thank you.
So we know that y equals 4, and then simply x plus y equals 5. And we know that therefore x plus 4 equals 5 and x is 1. So this is a quick practice for you. Same thing. Take a couple minutes and one of you guys can raise your hand. Tell me how you want to solve this. But 2y plus x equals 9. X plus 3y equals 10. And I want you guys to solve this with the same solving for one variable in terms of another. Don't use a different technique. So make sure you get that. And I'll call on one of you guys.
Which variable do you want us to solve for?
Solve for both variables. So do the
Okay.
same thing. Yeah, solve for one and solve for the other. Okay. Rashik, would you like to let me know what you think?
Yeah,
Okay,
I want to
so
solve this. Yeah.
let me quickly just transfer this equation onto. Okay, here you go. So these are our two equations.
So from the second equation, we got
Mhm.
x is equal to negative 3y plus 10.
Okay,
So I plugged that in the second equation and I got 2y minus 3y plus 10. And
okay,
then afterwards, I got negative y is
okay,
equal to negative 1. So y
okay,
is equal to 1.
okay. There you go. And how did you find x?
And I plugged y is equal to 1 into x is equal to negative 3y plus 10. And then I got x is equal to 7.
Okay, good job. There you go. Again, it's pretty basic. You guys probably done this a bunch of times, but it's important we get our fundamentals down and solid. I'll open another one later, but another base things you've probably done, I'm not sure, depending on what your level and grade is to find the zeros of an equation. So this is also termed like if you're given an equation, they'll just say solve this equation. It's really finding your zeros, which is another way to word it. So your zeros of a function are defined as when the output or y is 0. So I'm not going to get into there's a bunch of different techniques to solve your equations, but I'm just going to get into a couple because our actual math in physics does not get too complicated. It's more the physics part, the actual understanding how to solve different problems. So we don't need to learn all these advanced techniques again. I'm just going to go over one or two. But oftentimes we can factor to find our zeros. So for example, find the zeros of this function, y equals x squared minus 2x plus 1. So simply I can set 0 equals to x squared minus 2x plus 1. And we can factor x squared minus 2x plus 1 into x minus 1 and x minus 1. Therefore, because it is a repeated 0, we only have one 0 in this scenario. X is equal to 1. So another way to look at this in terms of physics is that at x equals 1, our certain value is 0. Our output is 0. So if we were looking at this in physics, normally when we look at an equation in physics, our x is going to be time. There are other variables that it could be, but oftentimes when we look at motion in physics, our x value is going to be time. So at time t x equals 1, the output, whatever it could be distance, weight, etc., is 0. So a quick practice again, take 3 minutes, find the zeros of this function by factoring. And I'll call in one of you guys in 2 minutes. I'm gonna call on Shiva Harish because I'm not heard from you yet. So let me know. 1 sec. Let me just open this paint. All right, let me know how you solve this problem.
So, wait,
Yeah.
so,
all right.
okay, so I use factoring, right? So I just factored
Yeah.
it,
Okay, so what did you find as your factors?
right. So my factors were,
It's okay, you can take your time with this one. You got it? If not, it's okay. I can call in someone else.
wait, never mind, I don't have it.
Okay, that's okay. Don't worry about it. Again, it's okay to make mistakes. I'm gonna call on Jayadeva.
So I just saved the zeros of the equation. Okay, so you can factor this out to x minus 10 times x minus 12.
Okay. There you go. Simple. Make sure we factor like this. So therefore, what are our zeros of this equation?
10 and 12.
10 and 12. There you go. Oftentimes, people make this mistake. They see minus 10 and they're like, minus 10 is our zero. That is not correct. You need to make sure it's the opposite of what the sign is. It's really what makes this term 0 and what makes this term 0. And oftentimes in physics, if time is our x, we are not going to be dealing with negatives. So of course, if you make a mistake like that, you'll know there is no negative time. But when you're not dealing with time, you might make that mistake. So just make sure we remember what makes this term 0. Is it negative 10? Is it 10? It's obviously 10. Very simple. Okay, there we go. Time, we're doing good. All right, now we can get into quadratics. So this is the quadratic formula. Many of you guys have probably seen this before, maybe not. So it is written in the term of x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So if you are familiar with this equation, you probably know how to plug in, how to find negative b, a, and c, or b squared as well. And of course, this diagram tells you right here, a is the coefficient in front of the x squared, b is the coefficient in front of the b squared, and c is your constant. So looking at that in an actual equation right here, just look at this basic form of y equals ax squared plus bx plus c. And therefore we understand what is our a term, what is our b term, and what is our c term. So if we look at, let me get to, if we look at y equals ax, if I write this in terms of ax squared plus bx plus c, I know that by writing it, this is just an example equation right here, writing, so let's say 5x squared, let's rewrite this. Y equals 5x squared plus 9x, we'll just go 9x, minus 12. This would be our a term. This is simple. This would be our b term. This would be our c term. And looking at our quadratic formula, if I just move this into looking at our quadratic formula, I can simply just plug in the values that I'm given. So if I know that b is 9, negative b is negative 9, plus or minus b squared, which is 9 squared, minus 4a, which is 5, and c, which is negative 12. All over 2a, which is 5. So this will help us find the zeros or the solutions to an equation. I'm not going to actually solve that, but we can get more into the quadratic equation. Our b squared minus 4ac term, that's known as our discriminant. So it really determines how many solutions we have. To find the actual solution, you're going to have to solve the whole equation, but just by looking at this one term, this b squared minus 4ac term right here, you're going to be able to determine how many solutions your function has. If that term in itself, just the b squared minus 4ac, you could ignore the square root. If that is greater than 0, we have 2 solutions to our equation. Sometimes it'll just ask how many solutions. We have 2 solutions. If it equals 0, we have only 1 solution. And if it is less than 0, we have no solutions, and that's when we get into imaginary, but for the purposes of physics, we do not get into that, so it has no solutions. It is the longest way to solve your equations, but it is almost always going to work. If you have a quadratic equation and you need to solve it, you can always plug it into this formula, and it is going to work almost all of the time. Of course, there are other techniques such as factoring, completing the square. I didn't go into completing the square, but those techniques also do work, but they do not work in every single scenario as a quadratic would. Another important thing when we look at quadratic equations is finding the vertex of a quadratic equation. This is very common in physics when we want to graph something. Is this something easy? Can we find this vertex? I do not need to plot all these points to find where the exact vertex is. Simply, we can use the idea that x is equal to negative b over 2a. We have our b and a values. We can determine those just by looking at our equation, plug them into this formula, and to find, that'll give us our x coordinate of our vertex. And to find the y, just simply the output of that. So we just plug in negative b over 2a for x and back into the equation, and we will be able to find our output value for that. And we will therefore have our vertex in coordinates. So quick practice, take 2 minutes. Find the vertex of this given equation, y equals 2x squared minus 3x plus 9. One person just asked if there's going to be a recording. There will be. So if you guys want to go back and watch it and understand these different equations, you're welcome to. Shiva Harish, you raised your hand. So do you have an answer for this question?
Yes, but yeah, I think yeah.
Give me 1 second. Let me just transfer this equation. Y equals 2x squared minus 3x plus 9. Okay, tell me how you found the vertex.
I didn't use the quadratic formula, but
Yeah.
I did use the some like I forgot what it was called, but like I did this, I believe. And then the x value is 3/2, right? Because like if you
Okay.
so if you square it, so I made it in a square equation. So if 2 in arrow 2, x minus 3/2 whole squared plus 9, I made it into another equation. And then and as for the y value, so x is equal to 3/2. So for the y value, I substituted, so 9 4 times 2. Okay, so that's, and I cross multiplied, so I did 9/2 plus 9, I think. I think that's how it works. No,
Okay.
don't.
Do you have anything else?
No, I just that's how I solved it.
Okay. So again, when we're looking at the vertex of an equation, we do not use the quadratic formula. We just simply use x is equal to negative b over 2a. You did a different technique. I'm not sure. I'm not familiar with that technique, but I believe your answer was not correct, at least for the x coordinate. But when we look at x is equal to negative b over 2a, all we have to do is simply plug in these values. You do not need to overthink it or try to go to a different equation. I think even if you're comfortable with a different way to find the vertex, this is just simply a much easier, much quicker way. You just need to look at these values, plug them in. So 2x minus 3x plus 9. So our b is negative 3 and our a is 2. So our x is 3 over, or negative, we can just write it as negative 3, but those really cancel out, over 2 times 2, which is 4, which is 3/4. Right? That is going to be our x value. And simply to find our y, we have to go in 2 times 3/4 squared minus 3 times 3/4 plus 9. And this is going to equal 8 minus 9/8 minus 9/4 plus 9, which simplifies to, let me just, give me 1 second. It's negative 9/8 plus 72/8, which is 60. All right, so our answer is just 63/8. This is our y coordinate, so it is 3/4 63/8. So again, as I said, even if you have a different technique, I would recommend using this. You do not, and just to clear up any confusion, you do not need to use the quadratic equation for vertex. You just simply use x is equal to negative b over 2a and find the y coordinate with the given equation. Even if you do know a different way, I would recommend sticking to this one.
Excuse me?
Yeah. What's up?
Wait, could you go back to the last slide?
Yeah.
So if 3/4 is squared, shouldn't it be like 9/16?
It is 9/16, but I just simply canceled it out with the 2 right here.
I see.
So I just canceled out 2 and 16 to get 8. And here, of course, it's not squared, but I just simply canceled out the 2 in my head. I may not have said that, but that's just what I did. I just simplified. Don't need to get an extra term here and have 2 times 9 over 9 over
I
9 over
see.
6. Yeah.
Okay, thank you.
So for our last concept of the day, we do have trig. So we do need to know a little bit of basic trig for physics, but the good thing is if you take physics and if you take tests, you are going to get your calculator. Whether it's scientific or graphing, you are allowed to use a graphing calculator, which does make your life a whole lot easier. Sometimes you will only be using scientific, but you will always have a calculator and always be able to perform trig functions. So you do not need to memorize actual trig values as you would for maybe a math class. But it is important to just understand where certain values or certain trig functions are 0 versus other values. It is actually very easy to memorize the unit circle. Sine of 30, 45, cosine 30, 45, 60, sine 60, etc. Because the values will eventually change based on only negative and positive signs. You're going to have this repetition of root 3 over 2, 1/2, root 2 over 2, 2, root 2 over 2, 2, and 1/2 root 3 over 2. You're going to have that repetition in some way in every single one of your quadrants. And you're going to have that 1, 0, 0, 1, negative 1, 0, 0, negative 1. So it's actually not very difficult to memorize your unit circle. But for the purposes of physics, you don't need to. But you could, because in a test, it may save you time when you are trying to answer a question. You do not need to enter it into your calculator. You know, sine of 30 degrees is 1/2, for example. So we can also look at a simple unit circle in this way, that our x and y coordinate are cosine theta and sine theta, respectively. We can just look at this diagram to explain it. But you do not need to get into proving functions, but this is just something there to conceptually sort of understand why x is cosine theta, y is sine theta, etc. But really, we understand that theta is measured counterclockwise from the positive x-axis. So this is your positive x-axis, this line right here. We measure our degrees this way. So it goes around this way. So this is 90 degrees. This is 180 degrees. This is 270 degrees. And then therefore this is 360 degrees, and it repeats infinitely. But sometimes common convention, not for math or anything or physics, but like sometimes we'll look at it, like for example, when you look at a clock, we think it progresses clockwise. But it's important to understand that our theta changes counterclockwise. And if we are going clockwise, we're going to be going negatively. For example, if we start here and we want to go clockwise, this is negative 90 degrees, negative 180, negative 270, negative 360, and it goes in that circle. But it is important to memorize it like this. We understand that again, as I said, x is equal to cosine theta, y is equal to sine theta. You do not need to get into proving these things are true. You just have to understand that x is equal to cosine theta and y equals sine theta in this scenario. And if we label x and y to be those things, we can find our definition of all other trig functions: tan theta, cosecant theta, secant theta, and cotangent theta. Simply, tan theta is sine theta over cosine theta, or y over x. Our cosecant theta is 1 over sine theta, or 1 over y. Our secant theta is 1 over x, or 1 over cosine theta. And our cotangent theta is x over y. For the purposes of physics, you will mostly be dealing with sine, cosine, and tangent. You may be asked for cosecant, secant, and cotangent, but it is very unlikely. But if you need to, it's a very simple conversion to get from either. So, and again, if cotangent theta is x over y, another way to look at that is cotangent theta is equal to 1 over tan theta. So again, it's a very simple conversion when we need to find these different things. Yeah, do you have a question?
I was just saying tangent and cotangent. I mean, they're just flipped the other way around, like
Yes,
arithmetic,
exactly.
So-
There.
because they just added a co in front. They just
Yeah, it is. It's simply just a flip. X over y is just another way to say 1 over y over x. So not too difficult. And another way again to look at basic trig, you can look at this. It's not too difficult to understand this, but when we look at our different tangent, cosine, and sine, when we look at a right triangle, this is the most common use of trig in physics. We can look at an inclined plane or a triangle of some sort. That's a right triangle. And we're given maybe some side lengths, maybe the angle, and we need to find the side lengths, etc. So sine is equal to sine theta, which is equal to the opposite over hypotenuse. Opposite over hypotenuse, in this case, b over c. Our cosine is our adjacent side over our hypotenuse. Adjacent over hypotenuse, a over c. And our tangent is our opposite over adjacent. So opposite over adjacent, b over a. That's just a simple way to look at it. You may not always get an income plane that looks like this. It may be oriented differently, but just always remember opposite hypotenuse, opposite adjacent. It's a very simple and easy thing to memorize when you're looking at basic trig. And I think one more concept I'd like to go over in terms of trig. Give me 1 second. Is being able to find an angle with given side lengths. So as I mentioned, sine theta.
I have a question.
Yeah, what's your question?
Do we need to like write these down like the thing you showed us? Do we need to like write it
You
down?
mean this right here?
Yeah.
I'd say it's a pretty good thing to memorize. It's not too difficult. It'll take a little bit of time. But I would recommend writing this down because you're not going to use it just in physics. You're going to use it when you take trig classes, in math, etc. Unless you maybe already taken them. But it is, I think, a good thing to memorize. But
Okay.
quickly, given that sine theta equals opposite over hypotenuse, so as you said, b over c. So I'm just going to write this symbolically. But how, and say we know these two side lengths and they are given values, but I'm not going to input them. Say it's like 5 and 6. How can I find this angle? So the easiest way is simply just writing theta equals sine inverse. This is another function on your calculator. So therefore you do not need to perform this math. The sine inverse of whatever 5 over 6 b over c, that will give us the value of theta. This is just a simple concept when we want to remove trig functions from one side of the equation to another. All you have to do is take the inverse of it and put it on the other side. Isolate that one trig function and take the inverse and put it on the other side. That's just something that you're going to also need to do in physics, mainly for sine, cosine, and tangent. So just an important thing to understand. When you want to find the angle, you're going to have to take the inverse of the trig function, put it on the other side of the equation. Let me see.
Excuse me?
Yeah.
Could you briefly explain what is sine, cosine, and tangent? I wasn't here like for some
Okay.
of the class. Yeah.
Okay. So when we look at it in this way, right here, our sine is our y and our cosine is our x. That is the most basic way you need to look at it for physics. You do not need to get into like proving trig functions exist. Of course, we do not need to waste our time doing that. When we're given physics questions, we actually operate on a much higher time constraint than math or other classes. So we do not want to get into that, but it's simply looking at it. X is equal to cosine theta, y equals sine theta, and tangent is just simply y over x. That's the most basic way you need to look at it for physics. And being able to apply it here in this triangle. Sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tangent theta is equal to opposite over adjacent.
Okay, thank you.
Yeah. So I noticed a few of you guys did have a few questions that I may not have gotten to. So I will get to those, but I think some of you guys might be in the 10 a.m. class as well. So if you need to, that is the end of our class for the day. I hope you guys understood what I was trying to teach. I understand some of you may not have. If you need to, reach out to me, ask me questions. This recording will be posted, the slides will be posted, and we will also be posting a quick assignment that needs to be done for before the next class. It's not going to take too much time. If you are not in the Google Classroom, you can send me an email, send someone in our Oregon email. We will get you the link. You can have a parent reach out, but we will get you that link. I will get to your questions that haven't been answered. But other than that, thank you guys for being here, and I will see you next class.
Bye. See you next class.
See you next.
Bye. Wow.